All right, let's go back to first-order differentials, specifically to homogeneous linear equations of the form ay prime plus by equals 0, where specifically a and b are constants, and we're just going to claim that a is a non-zero thing. So basically, a and b are numbers. This type of equation can be solved either by separation of variables or with the aid of an integrating factor, but there's another solution method, one that uses only algebra. So let's kind of manufacture a what-if scenario and kind of look and make a couple of observations about this. So let's say I've got one solution of e to the mx, and I just want to look and see, in the general format, what kind of patterns could I recognize with this? Well, if I take the derivative, y prime is m e to the mx, and if I evaluate that, so that would be a m e to the mx plus b e to the mx equals 0, and I factor out the e to the mx, that's going to give me am plus b equals 0. Okay, so write that a little bit nicer. Now, what about e to the mx? Is that ever going to equal 0? Nope, not at all. So that means the only potential solution that we could come up with is that component from the factored form, where am plus b has to be 0. Okay, so m in this case would be equal to negative b over a. Okay, so now we got a stronger sense of what our solution would look like in terms of the coefficients of the equation. So let's look at a specific example of this format and see how this helps us solve the differential equation. Okay, so in this one, 2y prime plus 5y equals 0. All right, we can kind of speed this process up because we know we're going to end up with essentially 2m plus 5 equals 0. So m in that case would be negative 5 halves. So the general solution then for what we've got so far would be c1 e to the negative 5 halves x. Okay, so let's broaden this out to the second derivative equations we've been looking at. So if we do that same analysis, where we set y equal to e to the mx, calculate y prime and then y double prime, evaluate it into our equation, we can factor out e to the mx additionally, and then we have a quadratic in terms of a, b, and c, and m, and this reminds us of the quadratic formula, so we can apply that. Now this gives us this am squared plus bx plus c. This gives us something called an auxiliary equation of the differential equation. And then just like solving the quadratic formula, we end up with 3 very distinct cases. And depending upon which case we're staring at, that tells us the type of solution that we would be dealing with. So in case 1, where b squared minus 4ac, so the discriminant, is positive, then our general solution would look something like y equals c1 e to the m1x plus c2 e to the m2x, or of course m is the solution to that particular quadratic equation. All right, case 2, where the discriminant ends up being 0, we would end up with initially our first solution being e to the m1x, and then using the previous method we figured out last lesson, we can solve for the second solution. That would be e to the 2m1x over e to the 2m1x dx, which equals e to the m1 x integral of dx, which is x e to the m1 x. Okay, so our general solution in that specific case where the discriminant is equal to 0 would be y equals c1e to the m1x plus c2 x e to the m1x. All right, and then the last case is when it's complex. So when the discriminant is less than 0, we end up with some complex solutions. Okay, so in this case, let's see, our solutions are going to look something like m1 as alpha plus I beta, and m2 as alpha minus I beta. So if we put that in the general format, we get y equals c1 e to the alpha plus I beta, and this is all x, and then c2 e to the alpha minus I beta x. And then we're going to pull up a reminder of some formulas. So we've got Euler's formula. And it's okay if you need to go look this thing up. That's fine. I'm going to walk you through briefly how it works. But Euler's formula says e to the I theta, getting ahead of myself, is equivalent to cosine theta plus I sine theta, where theta is some element of the real numbers. So some of you might see what's about to happen here, but so if I have, in our case, e to the I beta, the positive one, that'll break up into cosine beta x plus I sine beta x, and then the negative one, so e to the negative I beta would be cosine beta x minus I sine beta x. And pull out some identities real quick. So if you remember your even odd identities from trig, if I have cosine of negative beta, that essentially absorbs the negative. And if I have sine of negative beta, I can bring the negative out front, so that's equivalent to sine of beta x. Okay, so putting that with our e's, so if I have e to the I beta x plus e to the negative I beta x, that whole expression is going to simplify down to 2 cosine beta x. And similarly, if I have e to I beta x minus e to the negative I beta x, that's going to simplify down to 2I sine beta x. Okay, so put this all together. Put it right back to our general format for our general solution here. So when we said the solution to this particular differential was c1 e to the alpha plus I beta x plus c2 e to the alpha minus I beta x. If we apply all of those different identities we just listed out, we can rewrite this as c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine of beta x, which, if we factor out that e to the alpha x from each term, we end up with c1 cosine beta plus c2 sine beta. Okay, so in summary, if we have that second order differential, we've got three cases we want to look at for solving our quadratic, and each of the three cases has three formats of the general solution.